Hello and welcome everybody to the course Crystal Engineering Chemistry Beyond the Molecule. This is the last video of the series. During the last weeks and months we got insight in different areas of crystal engineering. And do you remember all the information we have heard? Yes. So I would say similar like a review of a year. Let us fly over the crystal engineering world and highlight some spots of selected topics. We start the lecture series talking about PP stacking and how you can use PP intermolecular interaction in crystal engineering. And I think it was the first example I have shown about example of crystal engineering, how you can really use properties of intermolecular interaction to design crystals. Very nicely shown here. Benzene and hexafluorobenzene both have similar crystal packing, but if you look to the electrostatic potential map, you see we have a reverse quadrupole moment, and you can use exactly this property to design a crystal, a co-crystal, and you see the switch of the intermolecular interaction. Now here have the stacking columns. This was the first example. This was the start. When we go on, have a look on hydrocarbons, aromatic hydrocarbons. And we have seen that the similarity is very, very important to describe and to analyze crystal packing. Molecules of a similar shape and size can take the same or similar crystal structure. We have seen that the ratio of hydrogen and carbon is important for the crystal packing in the case of aromatic hydrocarbon. And we have seen that the similarity aspect is not only restricted on this aromatic hydrocarbon. We have seen, for example, iodine and bromine substituted compounds very often have the same crystal structure. When we go on and talk about intermolecular interaction and we talk about supramolecular syntons, how we can use it, what it is. This is a unit of molecules and intermolecular interactions, called supramolecules, which can be formed and assembled by a known or synthetic operation involving intermolecular interaction. Yes. And when we said, okay, very important crystal engineering is the prediction of crystal structures, thinking about the crystal structure of suggested desired crystal structures. And when we said calculations are very helpful, but it's very important which calculation method you use. We have shown, for example, in this case here, CF3 substituted benzene. It is not helpful to look to the optimized dimer aggregates in the gas phase and use this result to analyze and interpret the crystal packing. Yes, and we have seen that calculation can help to understand intermolecular interaction, can help to understand what are the dominating interaction. We have seen in this examples that the distance in intermolecular interaction is not the dominating parameter. Very nicely. We have seen sometimes longer distance have a higher energy. So be careful by analyzing intermolecular interaction. Don't have only a look on the distance. When we have said we have a very powerful tool called CSD, Cambridge Structure Database, with more than 1 million organic structures inside. Yes. And it helps to understand so many things in crystal engineering, intermolecular interaction. We have talked about hydrogen bonds, we have talked about carboxylic acid. We have seen with carboxylic acid, this is a typical pattern, aggregation pattern of carboxylic acid called the dimers. But only around about 33% of carboxylic acid crystallize with such a unit. This was one point. The second point is that you can really say such pattern have characteristic parameters like angles. See it here, angles around about 180, 160 degrees, and characteristic contact lengths, distances. See it here, around about 1.6 to 1.8 or 2, whatever you want. So this database is really helpful for each person who is interested in crystal structures to help to understand the behavior in solid state. When we looked much more deeper in hydrogen bonds, and we saw there's a hierarchies of hydrogen bonds. The best donor and the best acceptor will form the best hydrogen bond. We have seen several examples. And when we switch on halogen bonds, very important in intermolecular interaction, very useful. Yes, and we have seen this is useful also in pharmaceutical industry. We have seen very nicely, in this case, for example, was one example here, the iodine substituents can be used as halogen bond donor. For example, with nitrogen heterocycles to form co-crystals. This helps. This improve the properties of this compound. Yes. And when we go on, we said, okay, we are talking of halogen. What's going on with fluorine? We have seen that fluorine by itself forms now typical halogen bonds, but you can use fluorine substituents. Yes, you can use it in crystal engineering, for example, to increase the acidity of neighboring hydrogen. And when this is helpful, for example, for build up hydrogen bonds with neighboring molecules. Well, we have seen very often, with only one example, very often we have seen that crystal engineering is not a sophisticated field of science. It's very useful for applications. We have seen, for example, here with the co-crystals, with saccharin, you can improve the stability. It was very nice. And this dissolution you have seen. Yeah. When we go on from fluorine we go on to hydrogen deuterium exchange. So we look for substituents which have really tiny effect on intermolecular interaction. Yes. And so we said, what's going on if we switch from hydrogen to deuterium has this tiny substitution variation, has this an impact of crystal structure, and we have seen it's possible, and it's known since a long time. See it here, 39, long time ago. Yes. When we go on, we talk about solvates and hydrates, the importance and the impact of hydrates, so water and solvents in crystal packing. We have seen that very often hydrates and solvates stabilize aggregates by forming intermolecular interaction, hydrogen bonds. Yes. On the other side, we have seen also non-polar solvents can be used in crystal engineering, filling the voids in crystal packing. When we talk about co-crystal synthesized strategies, we talk about how we can combine hydrogen bond and halogen bond, how we can successful, step by step, build up multi-component systems. When we have seen another strategy, this is the basic, is the different geometries, environments of the substituents, how we can substitute in this case. This case here, we have two different environments of the substituents here. The blue units here, different environments. Now we can substitute and we can once again build up multi-component systems. When we talk about polymorphism, this fascinating, sometimes mystery world of polymorphism, you see it here, all the different, there's only one component, ROY, yes, ROY, red, orange, yellow. This is the UPAC name, and all the different colors, and the only difference is here the angle, not more, yes. It's all the different colors and the melting points and so on and so on, and the habits. And we talk about, as I said, the mystery. So the disappearing polymorph. A polymorph form, first generated and suddenly impossible to reproduce it again. Disappearing polymorph. When we talk on general crystallization, different crystallization methods, we talk the importance of a metastable zone. Yes, metastable zone. How you can enlarge the metastable zone, how you can use the metastable zone. Always, first you have a task, you have aim, and then thinking about how you can solve the problem, your question. What is the answer? And very often when we must talk about metastable zone, how we can use it, at which point and why, and so on and so on. When we talk about mechanochemistry, yes, so this world of crystallization without solvents in general, but the difference of neat grinding, solvent drop grinding, liquid assisted grinding, something like this, and all, sometimes mystery. Sometimes one drops of a solvents is still enough to switch from one form to the other form. Very interesting topic. When we talk about pharmaceutical tasks, yes, once again, we talk about the importance of phase diagrams, binary phase diagrams. If you're only looking to compound and a coformer, yes, and when with ternary phase diagrams, now we have a drug, we have a coformer, and the solvent, and how important such phase diagrams are to figure out the exactly area. This is here, zone 3. This is the exact area where the co-crystal is really stable. So you must reach this zone in your experiments. Yes? When we go on looking to after hydrogen bonds and halogen bonds, we go on to chalcogen bonds. So looking for bonds in the 6th group, yes. And we have seen that is similarity to halogen bond. Also, in this class we can talk about sigma hole, yes. And we can use it in some examples. No? And at the end, we talk about additives, yes. Additives, how it's useful in crystal engineering to switch from one polymorph to the other polymorph, or use additives for controlled design of new polymorphs. Talking about tailor-made inhibitors, motive stop inhibitors, all of them to control the crystallization in a specific desired way. Well, that's it. And now you should be well prepared to design your desired crystals. Good luck and have fun in the crystal engineering world.